All right, so let's look at some common singularities. Some common singularities for 6 revolute joint, 6R open chains. Okay, so let's start with, I made a list here. Okay, so here's a common one. It's one I drew already. Okay. It's when we have 2 axes that are collinear. Okay, so 2 collinear, it's 1L. All right, one of these days I'll look it up. 2 collinear joint axes. Okay. All right, so let's say axis 1, axis 2, axis 3. So axis, and then we have 4, 5, 6 out there somewhere. I don't care where they are. Okay, so let's say axis 1 and axis 3 are collinear. Okay, so let's write down the Jacobian in this case. Okay, so remember, writing down the Jacobian is just like writing down the 4 kinematics using the product of exponentials, right? Write down the screws for each joint. Okay, so screw for joint 1, going to be some direction. Let's call it omega 1. Okay, and then screw axis 2, okay, some omega 2. Screw axis 3 is what? Minus omega 1. We'll call it plus omega 1. All right, plus minus omega 1, right? Doesn't matter. So it's actually plus minus omega 1. Okay, but just take plus. Okay, for this example. For this example. Okay, all right, so what goes here? Pick a point Q1. Okay, what is it? Minus omega 1 cross Q1. Okay, and something goes here. I don't care. What goes here? Minus omega 1 cross Q2. Okay, let's call it Q2. Okay, minus omega 1 cross Q2. And then we have 3 more columns that I don't care about. Okay, so here's my first column here. Okay, somebody's really excited about this. Okay, so S1 prime, S3 prime. Okay. So S1 prime minus S3 prime. Let's subtract the 2. Okay, we get omega 1 minus omega 1, 0. Down here we get minus omega 1 cross Q1 minus omega 1 cross Q2. So it's minus omega 1. All right, let's write S1 prime minus S3 prime equals 0, and then minus omega 1 cross Q1 minus Q2. Okay. Q1 minus Q2 is the same direction as omega 1. Okay, so this is 0. We get 0. Okay, so S1 and S3 are linearly dependent. Okay, so if we have 6 columns here, 2 of these, S1 and S3, are linearly dependent. Okay, they point in the same direction. So it can't be, so this matrix cannot be rank 6. Okay, so this is singular. Okay, so singular. Okay, now let's think about another case, this time involving 3 joints. So suppose we have this configuration, 1, 2, 3. Okay, so 3 axes are parallel and all lie in the same plane. Okay, so these are all parallel and coplanar. Okay, so 3 parallel and coplanar joints, R joints. Okay, these are all R joints in this case. Okay, I claim this is also singular. Okay, let's see why. Okay, so I can choose the base frame anywhere, right? I can choose the base frame anywhere. So let me choose the base frame, I don't know, say here. Let me attach it here. So, okay, so that's my base frame. Okay, now write down the Jacobian, G sub S. So let's say these are joints, joint axes 1, 2, and 3. Okay, and then we have 4, 5, 6 somewhere. Not important where they are. Okay, so first column, some axis omega 1. Okay, and then minus omega 1 cross Q1. Let me take Q1 to be the origin. So this is 0. Okay, and then joint axis 2, same direction, omega 1. Okay, so this is minus omega 1 cross Q2, some point on joint axis 2. And then omega 1 minus omega 1 cross Q3. And then I have 3 more columns here, which I'm not going to worry about. So let's look at these 3 columns. Okay. So these are all the same. Okay, so you look at these 3. Okay, and now you can see that, right? These are 3-dimensional. 3-dimensional. This one is 0. Okay, so there's no way this can be, right? This can be linearly independent. Okay, so these 3 vectors are not linearly independent. Okay, so it's a singularity. All right, and these also come up quite often, right? If you have a 6-axis standard 6-star manipulator and the arm is completely extended, right? Then you have these wrist joints that are parallel to the elbow joint and the shoulder joint. Okay? It's a very commonly occurring singularity. Okay, now let's take one that's a little bit less intuitive than these. Okay, so now we're going to take 4 revolute joint axes. They intersect at 1 point. Right, so here's the situation. Okay, and then we have So I'm going to okay, all right, not bad. I may say so. Okay, so we have 4 joint axes that intersect at a common point. So where are the axes? Well, here's one. So here's the point of intersection. So here is, all right, I want to make sure that these, all right, so I take it back that this was not bad. Okay, so let me do it that way. Okay, so here's axis 1. Right there. Axis 1. Axis 2. Okay, axis 3. And finally, axis 4. Okay, so 4 revolute joints intersect at a common point. Okay, so 4 R joints intersect at common point. Okay, let's see. Is this a singularity if you think about it? So here's my shoulder. Okay, so that's the configuration. Well, let's do an analysis. Okay, so J sub S all right, easiest thing to do here is, remember I said I can put the base frame anywhere. Okay, so easiest place to put the base frame for this problem is, let's just put it right here. Okay, so pretend the base frame is there. Okay, now if I do that, then it's very easy to write the Jacobian. Joint axis 1 will have some omega 1, 0. Okay, omega 2, all right, it's going to be something. And we'll have something here. Omega 3, okay, something else here. Omega 4 here. What do we have? Minus omega 4 cross Q4. Just pick the origin. 0. Omega 5, 0. Omega 6, 0. Okay, that's what my Jacobian looks like. So let's focus on this, that, that, and that. Okay. Okay, so, right, you can just look at this for 3 seconds, right, and you immediately realize there's no way these 4 vectors can be linearly independent. Okay, so these 4 are not, okay, linearly independent. Okay, so singularity. All right, so remember we said that at a singularity, the end effector loses 1 or more degrees of freedom of motion. Okay, so for example, if the arm's this way, right, I can't move in this direction. Okay, if the arm's completely folded, I also cannot move this direction. What are we losing here? What are we losing here? So imagine the wrist is right above my shoulder. Okay, so I can move in the x direction. move in the y direction, z direction. I can rotate, right? This axis, this axis, this axis. What are we losing here? What are we losing here? Okay, what did I do here? I'm using the wrong model. I'm using the wrong model. My arm is not this. This is not my arm. Where's the difference? Where's the difference? My shoulder has 3 joints. Okay, my shoulder is a spherical joint. Here we have only a 2R joint. Okay, so my arm has 1 more degree of freedom than this. My arm is 7 degrees of freedom. This is 6 degrees of freedom. Okay, so if I somehow remove 1 degree of freedom, what I cannot do is I am now unable to move. All right, so this is going to be tricky. Let me try drawing it. So here's the plane. Okay, so this is a plane containing these links here. This link and say that link. Okay, so the plane defined by these 2 links. Okay, if you think about it, this configuration, I cannot move this point in a direction normal to the plane. Okay, so if I'm this way, all right, with this robot, I'm unable to do this. Okay, I can't move in directions normal to this plane, whereas my arm can, right? So, so actually having extra joints is a very good thing here. Okay, so imagine, hundreds of thousands of years ago when our ancestors were, living in trees, swinging, grabbing fruit, Suddenly you're in this configuration, and you need to catch a limb to swing across, Oh, I'm at a singularity. Not good. So evolution helped us, gave us an extra degree of freedom here so that we can actually grab fruit and swing from trees and so on. Okay, I think this is a good place to stop, so let's stop here.